Interval analysis is a numerical analysis method. It was introduced in the 1960s to perform calculations that guaranteed accurate and reliable results. At the time, many applications presented problems that were very difficult to solve reliably using conventional numerical tools. Research conducted by the COPRIM project team is based on interval analysis, which can be explained most simply by studying an example. Let's assume we are trying to solve a two-equation system with two unknown values x and y in a bounded domain. The unknown values x and y represent a physical quantity. For example, they could represent the position of a robot's hand in a plane. In this view, the height of a point represents the value of the function f1 for different values of x and y. And this is the graph showing the function f2. Here we have plotted a plane at a height of 0. The blue curves indicate points where f2 equals 0. And the red curves the points where f1 equals 0. The blue and red curves intersect at those points where f1 and f2 have a value of 0. These are the system solutions. Here, the physical signification of the unknown values in the system means we must find solutions for x and y that lie within the interval -10, 10. From now on, we are no longer working with numbers, but with intervals. That is what interval analysis is all about. This box represents the domain in which we shall look for solutions. For a given box, interval calculation is used to obtain two numbers, a1 and a2, for each function f, so that the maximum value of f is not greater than a2, and the minimum value is not less than a1 for any point selected in the box. Interval analysis ensures that a1 and a2 satisfy this property, even if they are calculated using a computer that only provides approximate calculations. If we perform the calculation for f1 in the box -1, 1 by -3, 2, the result obtained shows the planes surrounding f1 are situated at -8 and -1. In practice, this means that the greatest value of f1 for this box does not exceed -1, and therefore f1 cannot cancel itself out for this box. The algorithm uses the bisection method. The principle consists of dividing the initial box in two, and then successively repeating this action for each of the resulting boxes. By applying interval calculation at each stage, we can identify and eliminate any boxes that do not contain a solution. The initial box B0 is evaluated using both functions. Because the values for planes a1 and a2 have opposite signs, it cannot be eliminated. It is therefore divided into two sub-boxes, B1 and B2. Box B2 goes on the stack. It shall be processed later on. The algorithm examines box B1. A'1 equals -9, A'2 equals 93 for the function f2. A1 equals -25 and A2 equals 15 for the function f1. It is possible that this box contains a solution. Therefore, it is again divided into two boxes, B3 and B4. Box B4 stays in the stack. It shall be processed later on. For the moment, the algorithm examines box B3. For box B3, the planes surrounding f2 indicate that it does not contain a solution, since the values of planes a1 and a2 are both positive. B3 is therefore eliminated. Bisection is a very rapid process that allows us to obtain increasingly small boxes. Once a box is sufficiently small, we consider that we have found the approximation of a solution. For this box, for example, the planes surrounding the two functions have a height very close to 0. We therefore consider that this box contains a solution, and will use more advanced mathematical techniques to confirm this assumption. Even more importantly, no solution can escape us. But interval analysis goes far beyond solving equation systems. This method can be used for a significant number of applications. It guarantees results despite the rounding errors inherent to computers, and can even manage the uncertainties of physical parameters in the design and analysis of sophisticated systems.